Yes, can you see my screen?
Yes, we see your screen. I'll give you a 5 minutes heads up when your time is finishing.
Okay, perfect. Thank you, Andrea. So, good morning, everybody. I will present quite quickly the payload design of the Hermes mission, but also the baseline for the payload for the Spirit mission that will be presented tomorrow by Michele Trenti. So let's start from let's say the scientific and budget requirements that Fabrizio already uh, explained. We needed to develop an instrument with a sensitivity, with a very good sensitivity, better than 2 photons per square centimeter per second, an effective area larger than 50 square centimeter, um, very wide energy band going from, let's say, soft X-ray to gamma rays, and with a medium good energy resolution for both the X and the gamma regions, a very good time resolution and presented for this kind of experiments, and also a very good time accuracy. A large field of view, low background, and all these requirements in a very constrained environment. That means volume smaller than 1.25, but let's say 1 unit, that is 10 by 10 by 10 centimeters, mass lower than 1.8 kilograms, and less than 5 watts of total power, of peak power. And also we have to cope with the radiative environment of low Earth orbit, both equatorial for Hermes and sun synchronous for Spirit, with a passive thermal control, and using mainly not space qualified components due essentially to cost limitation margin. And we aimed at obtaining good reliability, higher than the standard CubeSat, and some redundancy where it was possible, and also all the payload design was made with an eye to the mass production, because the ultimate aim of Hermes is uh, to reach a very crowded constellation. And so let's say how uh, the payload is made. Essentially, the detector working principle. In order to reach a compact and lightweight instrument with a very wide sensitive band, the option was to go for what is called a C-switch concept. That means a detector made by a sandwich of a silicon detector and a scintillator crystal, in particular a silicon drift detector and a GAG scintillator crystal, which, which is able to directly detect the X-rays in the silicon drift detector, and to convert the gamma rays in optical light, again read out by the silicon drift detector. Uh, mm, to make that work, we had to design specifically design a silicon drift detector for the same, and also to design custom front end, back end ASIC, and back end power supply electronics, and everything in a very compact way of the detector is only 3 centimeter thick. So this is the overall 1 unit of the payload, and with all the um, elements, the key elements. I don't know if you can see my pointer. This is the detector assembly made by the front-end electronics, the ASIC, the silicon drift detectors, and the scintillator crystals. covered by an optical filter to avoid optical and infrared and near UV light to reach the silicon drift detector. Then we have a backend electronics, which is in charge of interfacing the detector and also providing a very precise timing. The power supply unit, which provides power um, and the chap control for the whole payload, and the payload data handling unit, which is the onboard computer. I won't go in details of the composition, but in the slides you can find all the description of the components and also of the overall interfaces between the payload, which is this part with together with the front end and the satellite bus. So let's see some key elements. Let's start with the silicon drift detector, which are state-of-the-art detectors achieved in the framework of a large Italian collaboration, which is called Rexox. And thanks to the strong synergy between the INFM, Trieste, and FBK, for the design and production, and for by ASI, INAF, and ENFN for design consolidation and space qualification. These are now also the baseline for other instruments, for example, same technology, for example, on AXTP, the Chinese European mission for the LAD and WFM instrument, and also for XG's onboard Theseus. The design has been optimized in order to reach good energy resolution and low energy threshold, so noise, some kind of modularity. Yeah, was very difficult to cope with the complexity and the integration procedure of the detector. So also the size of the detector and the number of cells on each detector was optimized in a trade-off study, and take into account both this and also the time resolution, because being a drift detector, there is some drift time then impacts on the time resolution. And also the design was optimized to allow for the X-ray and gamma ray discrimination. That means discrimination between photons absorbed direct in the silicon in the crystal, and this was done by multiplicity. Each crystal is read out by two SDD cells, so gamma rays will give a signal, simultaneous signal, a coincident signal on two cells, while an X-ray signal will give an X-ray photon will give a signal only in one cell. And also, of course, we had to cope with low power consumption and not too high bias voltages in order to develop the electronics. Also for the scintillators, we did a trade-off study. Here are some common scintillator like sodium iodide, cesium iodide, etc., BGO, and gag crystal have some important advantages. They have high stopping power, they are fast, and also the peak lambda, the peak lambda peak for optical emission is well coupled with the silicon quantum efficiency. They are not hygroscopic and not radioactive, and also they are radiation tolerant. Although there is no flight proof so far, we performed also proton irradiation in the framework of the HERMES project to verify uh, the tolerance, radiation tolerance of the crystal, and also the afterglow, and also the geometrical design, surface finishing, and wrapping procedure was optimized in order to obtain the higher light output as possible. That means that translate in a better energy resolution and lower energy threshold. So putting together the silicon drift detector efficiency for X-ray with some dead layers like the optical filter and multi-layer insulation, with also the effective area of the crystals. This is the total effective area between 2 kV and 2 MeV, essentially, with a peak higher than 50 square centimeter and a very good wide energy response. Also the front-end PCB and readout ASIC were specifically developed for this aim. We started from the heritage in designing and developing ASIC for silicon drift detector of Polytechnic on Milan, also in the Rexos collaboration. And from the Viga ASIC, we, let's say, subdivided the ASIC in two parts. One which includes the preamplifier and the first shipping stage to be bonded directly to the SDD anodes and to be put very near the SDD anodes in order to minimize the noise, and the backend ASIC to be placed on the lateral side on the front-end PCB that are on a Rigiflex configuration, and with a very let's say difficult work also to limit the possible crosstalk between channels due to the fact that all signals come through these very thin 3 millimeters ribs on the front-end PCB, so all the traces are close, and this was made by changing the by implementing a current interface between the front-end ASIC, linear front-end, and the back-end ASIC. Everything in with a very large energy range and with low power and low noise, and also developed in typically radiation tolerant technology, which is AMS 0.35. Same thing, the same custom development was performed for the backend and power supply boards with some with a particular care on the redundancy and on the on avoiding single point failures and also to take to cope with the use of COTS component. That means most components are not cell immune or cell immune, so a very complex latch-up protection circuit was developed for all the power lines, and also all the power lines were subdivided in 4 quadrants, each one powering 1/4 of the detector assembly.
Yuri, 5 more minutes. Sorry.
Okay. So also the timing architecture was developed in an innovative way, having the GPS data going to the PDA2, while the PPS data signal coming from the DS bus going to the backend, where an integrated atomic miniaturized atomic clock produced by Microsemi, that is called CSAC, is placed, and this atomic clock use the input PPS to synchronize locally synthesized PPS, which is provided to the FPGA and to the and back to the PDA2. Also, the CSAC provide a very stable 10 MHz clock, and both the PPS and 10 MHz clock are used in the FPGA for accurate time tagging of the events read out by the front-end ASIC. Overall, this means that the time accuracy is very good, is less than 60 nanosecond when the PPS and GPS are locked, and of the order of 180 nanosecond if the PPS is unlocked and for a duration less lower than 3000 seconds, and the time resolution is also very good of the order of 300 nanosecond for the X mode and of 200 nanosecond for the gamma ray mode. Last component of the payload is the PDA2, which is the payload computer and is based on a board developed by ISIS called IOBC. There are some characteristics of and the task of the PDH are the interface to interface the payload with the service module to manage the operating modes, to create the photon list and buffer all the events, perform photon list cleaning, and also perform the bus trigger logic and the scientific formatting and housekeeping formatting, and to interface the atomic clock. Okay, I will skip um, the operating modes to go to the scientific telemetry, which is subdivided in essentially in three parts. One is the scientific rate meters that are continually produced and stored and are ready for prompt radio transmission in case of a trigger. These rate meters include, for example, count rates for 4 quadrants, 3 energy bands, and 7 time scales. A background produced photon by photon and also stored photon by photon in the energy range 5300 kb, which is always stored, and a photon by photon full band photon by photon data produced in case of a trigger, which with a pre-bus and post-bus programmable time frame, which is of the order of 50-100 seconds. Everything going in a total telemetry in case of 3 bus per day of less than 1 gigabit per day per satellite. Mass and power budget, very quick, is 1.6, less than 1.6 kilograms with margins, and less than 5 watts with margins on the demonstration model, and everything was measured on these demonstration models that was developed in the last months, integrated in July, August, which is totally, completely representative of the real payload from a mechanical and thermal point of view, and but only one quadrant is equipped with working detectors. So this allowed us to measure performance, also to perform some environmental tests. 4 detectors were installed with flight module representative performance, very low leakage current at room temperature of the order of 50 picoamperes per cell, and this allowed us to obtain very good results in terms of energy resolution for the X mode. Is measured both beginning of life, so at operative temperature of the detector, and end of life, so increasing the detector temperature to simulate the radiation damage induced leakage current of the detector at the end of the 2 years of the mission. The gamma ray spectrum of cesium X-ray source, and also low energy threshold lower than 2.5 kV for the channel, without this plot is without any equalization that can be performed thanks to the programmability of the single channel threshold on the ASIC. Also, the detector, the demonstration model was tested for vibration at the beginning of October at the Polimi shaker facility using Ariane 5 qualification levels, and then we performed the performance and functional test after the vibration with and everything was perfectly fine. So these essentially validate the mechanical design, and also the thermal design was validated by a thermal balance performed again Polymi thermal vacuum facility at the first week of October, and also this validate the thermal design of the detector. So essentially, we are now ready to start the production, the integration of the first flight module. Okay, thank you. That's all.
Okay, Yuri, thanks a lot for a very nice presentation. I don't see at the moment any question, but we can wait.